So we should today we go into the CL4. We go into ceramic and composite first. Then the last section will be polymer. So we are now in the last chapter, chapter 10. Chapter 10 have three section. So we will study ceramic and composite. Then the last one will be polymer. Okay. Okay. So your test 2 will be in week 12. You are now in the week 10. So next week I will let you know your scope. Then week 12 will be your test 2. Okay. Individual assignment due week 13. Okay. Lab report due week 12. Final exam 4 questions. If not mistaken, already come out, right? The final exam. If not, then you need to check. Okay. So we go into ceramic first. Okay, so ceramic, they are inorganic, non-metallic material. So these are the definition for ceramic material. And for ceramic, it can be divided into two main category or two group: traditional and structure. Traditional is what you see in the common daily life, clay, all these things. Structures, they are more used in the engineering application, right? Like for example, the gear, even some of the dental application. Okay, so the property of ceramic material, they are hard, they are brittle, easy to break, under certain condition. They are very good in compressive. Yeah, they are not good in tensile loading. Okay, if you pull ceramic in the tensile condition, they'll easily break. But if you compress them, it's not very easy to break the ceramic material. So these are their traditional properties: hard, brittle, low toughness, and ductility. However, structural ceramic, they are more harder than the traditional, stronger, tougher, right? Okay, so they are good insulator for ceramic. They are good insulator because they don't have the conduction electron and relatively high melting temperature, high chemical stabilities. So that's why they use in the engine and all these things. Okay. All right. Now recap previously in metals or pure metals, we learned about what is ionic, what is covalent. So in ceramic also we have. So as you see on the table here, with all sorts of names, ceramic compound, formula, melting point. So their melting point is higher than all the metals. You can see 4,000, 2,000, and so on. Usually metal will melt around 1,000 something, right? So these are the electronegativity different, percentage of IC, ionic character, covalent character, right? Okay. So now the rest you read. Okay, so how the ceramic, how they do the packing of ion. So there are two factor. One is the ion size, and one is the charges. Okay, relative size of ion. Another one is electrostatic charges. So these are the factor for ceramic. Okay. Now recall the coordinate number. You learned about this one previously. Coordinate number is how many sphere surrounding the solute. Okay. So Like for example, this one is stable. You have Cn of 4, okay, 4 sphere around the dark blue. This one also consider stable, but if there is a gap, then it becomes unstable. Okay. So coordination of anion with this negative charge, and cation in the middle is positive charge. Because positive charge cannot moving, cannot move. So only anion can moving. Okay. So the next formula, or first formula for today, will be ratio. Oops. So we learned about critical ratio previously. The radius ratio will be R, or positive R, and negative R. We take the radius of positive charge and divide it by negative charge. So you need to find the critical radius for these things. So if you plus the word critical, it means you want to find where it's stable state. Okay, stable state where it give you coordinate number, Cn, that you need to somehow memorize for your test. So a range of cation ratio to anion ratios. So range of the ratio, positive charge to negative charge. So this one, if this is your solution or your answer, answer for this ratio, if your number is more than 0.732, your Cn number will be 8. Means if you do the calculation R positive divided by R negative, if you get number more than this number or near to this number, near or equal to this number, means the surrounding will be 8, like the one you see on the diagram here. So you see the gray color surrounding by the 8 sphere. Okay. Second magic number will be 0.414. Your Cn will be 6. The third number will be 0.225. Cn number will be 4. And if it's 0.155, will be 3. Okay. Why we are not interested to find less than 0.155? Why? Again, we are more interested in stable state. The Cn is a stable state. When you want to surround one sphere or positive charge, you need at least 3. It's like you arranging the atoms, at least 3. 2 cannot, 2 it's still not stable. You're able to run here and there. Okay, so this 4 magic number you need to memorize before the exam. Okay, 0.7, 0.4, 0.2, 0.15. Okay, what happens if you calculate ratio? You get 0.234. If your solution is this one, what is the Cn? If your ratio you get 0.234, what is the Cn number? 4 lah. So it's between here. Okay. So either 4 or 6. No 5. Either 4 or 6. So if the number is 0.234, which is 4 within here, then it's 4. If your answer is less than 0.155, you need to check again. So if you get answer less than this number, something is wrong already. Okay. So these are the another illustration of our days. At least they are 1. You get less than that one, you can just put 2 lah. Okay. Actually, yeah. Okay. So if you get less than 0.155, you just consider CN number is 2. Right. So in exam, we won't give you this simple case one. Right. Maximum is 1. Maximum number is 1. 1 means this number same with this number. So if this is 1, it means the same size. The size radius is actually same. It's very hard to find the same radius one. Unless you find isotope or all these similar crystal structures. Right. Okay, so since we give you the 4 magic number, can you find from example 1 what is the CN number? Okay, calculate critical minimum radius R divided by R, or positive charge radius divided by negative charge radius for triangular condition CN3 of 3 anion of radius R surrounded by the central radius R in the ionic solid. Okay. So this question is asked you from CN here. So when the CN is here, we expect your ratio is more than 0.155. So you know there's 3. So you need to draw the diagram. You need to draw this one. Okay. Then you do trigonometry calculation. Okay. You need to draw some diagram like the one you see on the screen here. Okay. So in the middle, positive charge surrounded by 3. So they must be stable. Stable means they must be touching the boundaries of each other. If they split, means non-stable. So in your diagram, please make sure you touch, the line is touching the surrounding one. If you draw a dot with 3, I will just label non-stable. Then I won't mark already. Yeah, take note this one. So remember, if you draw something like this, and you just give me 1 dot like this is wrong. This is wrong. Not stable. So it must be touching the boundaries. So when you draw this CN3, and then you label ABC with the center of the sphere, and there's a E there just to help you to derive the trigonometry equation. Okay. So you are given the radius. So A to C is small r or big R? A to C. A to C is small r or big R? Capital R or small r? So it's a capital R. So you got 2R here. Capital R here, capital R here. So you have 2R. Here to here is R. Here, you don't know. But you know here to here, you know AE. A is what? A is what? Small is wrong. A is what? A is not small r. A is what? How come got small r? A equal? AE equal what? Huh? Huh? What? Not 2R? What mean by capital R and small r? Yeah. So small one is what? Positive charge ma. Big one is negative charge ma. So A equal what? A equal what? Not R, not capital R, but equal what? What is the equation to get the length of AE? Huh? What? What? Huh? Yeah. So is what? So you should write what? Capital R plus small r. This is very basic mathematics. Okay. So you have AE equal to R, capital R plus small r. You know AE, sorry, AD, not, sorry, I label wrong. No wonder you answer wrong. Okay, AD, not AE. AE is capital R. AE is here. AE is here. Okay, so AE is capital R. Sorry, AE capital R. AD is capital R plus small r. Okay, so you have a triangular. This is R plus R. This is capital R. You don't know this one. This is 90 degree. So you know that AC, CB, BA is the same length. So same length, you have 60 degree east corner. Okay. Then these two sides is the same. These three sides same. So DAE will be half of the 30. All right, so here will be 30 degree. Okay, if you enlarge your diagram, AE will be capital R and AD will be capital R plus small r with 30 degree. You want to find, the question asks you to find the R negative divided by R positive. So AD equal to R plus capital R plus R. So cos 30 equal to AD, cos 30 equal to AE divided by AD. And you manage to find this calculation because at the end, you need to find small r divided by capital R. So rearrange the equation, you get something like this, but still you need to get in small r divided by R. You need to rearrange it left, right. Okay, so this one you move to the left, 1 minus this one, you get this one. So at the end, you get R equal to R divided by capital R equal to 0.155. Okay, so as example 1 sure won't come out in exam because already give you in the class. Try to think what if it is 2, what if it is 4, what if it is 6, what is 8. Okay, so I already show you how to do 3. What happened is 4. Yeah, very high chances this one will come out. Any question for example 1? No, okay. Number 2. Okay, then you need to check your answer. 0.155 is what? CN number 3. If you get not what 0.155, you get less than 0.155, you get 2. Means you're something wrong with your trigonometry diagram. Or in the early, you already draw the wrong diagram. Yeah. Okay. So this is how you get the numbers. This is how you get the y 0.732, why you get 0.14, why you get 0.225, why you get less than this one. Because you are using example 1 approach by using trigonometries. Yeah. Okay, example 2. You are given positive charge, negative charge radius. Try to predict the CN number. So CN number for CSCl, NaCl, use the following radius. Do this as your exercise. Okay, so the first one will be what? CSCl, positive, negative. So you want to find the CN number, you need to find the ratio. You need to find the critical ratio, radius ratio. R negative divided by R positive. So the first one will be what? CSCL will be? What do you get, the first one? 0.93 something. Okay. So 0.93 will be, CN number will be 8. Because this one, you need to, if you calculate this one, you need to write 0.93 something, bracket, more or equal 0.732 CN 8. Okay, this will be the complete answer. Number 2, NaCl. What do you get? 0.564 will be more or equal 4.14. 0.414 CN 6. Okay, you need to show the working. Okay, you need to write something like this, like what you see on the screen. Remember the unit. Remember to write the unit in your answer. So the first one is 0.9 something, 93 something, 3 decimal place or 3 significant figure. Okay. So the first answer will be CN number 8. NaCl, if you do the same, you get 0.56 something. So number will be, CN will be CN will be 6. Okay. Okay, so the name of the 8643, 4 will be tetrahedron, 6 will be octahedron, 8 will be cube, 2 will be 3 will be triangular, 2 normally not stable, normally, not very rare to find. Okay, so if you understand example 1 and 2, you should able to do your test 2 test 2 of final exam. Okay, so this is more on the CN value. Processing, this one is just for your info just for your info. How to do ceramic. Okay. In Malaysia, which states famous for the clay things? This is fan, not ceramic. Which state famous for ceramic? Got ceramic? The labu things, right? The we call Perak. Perak, meh? Perak or Johor something some, I think they are Perak. Okay, so but anyway, you should able to talk to your international friend when they talk about ceramic. So at least you know some tourist spot or some famous spot that doing these ceramics. Okay, this is a traditional ceramic. Of course, more advanced one will be in the advanced manufacturing in Malaysia. So you need to prepare, then you do forming or casting, then you do thermal treatment, okay, or we call it curing. So ceramic, you need to do one thermal process. So You see from the loose powder until it become a pack, closed pack clay. Okay, so this one you read lah for your information. For information. Okay. So these are the tools they use to press the clay. Okay, then you go into the furnace. Okay, these are the another diagram. You do the pressing. This, if you see the word isostatic, iso means equal or same, right? Static means fixed. So isostatic pressing means you press with a constant pressure. Okay, so after cold pressure pressing, the part must be sintered. Sintered. So sintered is the word of thermal curing for ceramic. You only see sintered, this word, in ceramic material. Okay, the rest is your reading. Hot pressing. Hot pressing means you involve the thermal already. So this is the machine. If you go to industry and they're doing ceramic, this is a hot pressing machine. So what they do is they have a pressure inside here. They can heat up the material and so on. Okay. So this is a very traditional forming. This is called slip casting. You have a mold, then you pour the slip. The liquid for the ceramic is called slip. Pour in the slip, then you will take the form of the mold. Then you pour it out again. You pour it out, there will be a layer sticking to the mold, and then you remove the mold. Okay. It's called slip casting. Slip casting. Okay, the rest you read now. This also slip casting. Another more detail how slip casting is done. Right, you mix, you pour, then you pour it out, drain the things out. So you have a solution here, and you see the mold can break into two half. Okay, a design of the mold also another skill set in the industry. It can be metal mold or other ceramic mold. So draining, then you go into the curing and you get the products. Okay. Extrusion is like playing they call it what, clay or something. The kids' toy. You mix different shape. So if you see a machine with a cross section with the screw head here, it means this one screw head in engineering and with the channel here is, we call it extruder. This is the extruder mechanism. So when you turn the thing, if you turn, it will press the material to the front. Okay, so this is a extrusion mechanism. Thermal sintering. Okay, so when the sintering happen, the two sphere, they will melt and form the neck. They will join together. Okay, like a sweet, like a chocolate sweet. Then you melt them, they will join together. Sintering, this will be under microscope. You see the shape of the granular, right? This is another process called vitrification. Vitrification is the glass phase liquefies and fill the pore space in the material. Okay. So this process, vitrification, there is a glass phase transition. You heat it up, then they will go through the glass transition. This is why there's a glass transition. In ceramic, there will be Si element, silicon element. Okay. So this one will be ceramic.
Gaya Forest.
So this one you go and see lah. So it's a 9 minutes video. So go and see. You just copy this link and then you play lah. Okay, these are the sample of material properties for ceramics. Compressive strength. Just now, why we only focus on very highlighted the compressive strength rather than the tensile strength. You can see a bit like 10 times difference. Because ceramic is not good when you pull it, but it's very good when you compress it. So that's why your car automotive, the cram for the brakes, your ABS mechanism, you use ceramics because they are good in compressing and they are good thermal insulator. Okay, okay, the caliper lah, the caliper, right? Okay, so in ceramic we use fracture toughness. There's one term here called fracture toughness. So these are the defect inside ceramic. So don't confuse this one with the metals. Metals, you have point defect, you have line defect, you have a granular defect, and all this. So this one is more on ceramic. So as you see from here, it's quite direct. You have interface flaw, you have crack, you have unjoined edges, you have surface damage, you have pores here. Pores means hole. You have inclusion here. Okay, the rest you read. The rest you read. So these are the sources of a void or fracture. Why crack can happen. Pores also, this one you read. Okay. So these are the factors that affect the strength, the composition, microstructure, surface, and temperature. Okay, and environment. Environment here means if you're near to the sea, something will happen. If you're near to the corrosive environment, or acidic or alkaline environment, then it will be different. Okay. Okay, so this will be the fracture toughness. When you see this diagram, you should able to think of your impact test. Okay, so there will be a defect here, a control defect here. So the first, I think the second equation. First equation is the radius ratio. Second equation is ceramics fracture toughness equation. KIC. KIC means IC. The first I is type 1. We have learned type 1, type 2, type 3, the way you open it, right? Type 1 is like crocodile things. You look back like the previous slides, got 3 types of fracture. Type 1, 2, 3. Okay, so one KIC, the one is a type 1 fracture. C is critical, equal Y sigma failure square root pi A. Again, A is the H, the crack size. Okay, you have seen this one actually before this in the defects chapter. Okay, so we apply this equation, then we have a short break. Okay, example 3. Okay, KIC equal to Y sigma F square root of pi A. So the reaction bond of silicon nitrate ceramic have a strength of 300 megapascal and the fracture toughness is 3.6 megapascal square root of meter. What is the largest internal crack that in this material can support without fracture? Use Y equal 1 in the fracture toughness equation. So if the equation or if in the test you do not see Y value, you need to write assume Y equal to 1. Okay. So you are given KIC, you are given Y, you are given failure strength. The only unknown is A. Okay, rearrange this equation, find A lah. Okay, can just be careful every time you see crack. There are two types of crack. Just a reminder. One is at the side, one at the middle. This is called internal crack. This is called edge or surface crack. So this is A, but this is 2A. So this question asks you what? Internal crack. So when you find the A, please multiply 2 to solve the example 3. Just take note lah. This will be the careless mistakes. You solve. Why? How come I solve already, but I don't get the full mark? Because you don't answer the question. The question asks you internal crack and not surface or edge crack. Okay, you put in there just for your info. So remember the answer, you need to multiply 2 because it's internal crack. Put your answer in micron, 91.6 micrometer. If you are not very good in the index, the prefix, then you write in 10 power something in meter. Okay. Mechanical properties, this one you read lah. All these are application of ceramics. So like dental, all these things. Try to memorize like 3 examples of ceramics. Application of ceramics in daily life. This one usually if the ceramic question come out, A will be ask you to define ceramic and then give 3 examples of application of ceramics. So remember 3 lah. If it's not in my slide, you need to go and Google a little bit, then give me. Okay. This one will be in zirconia, PSZ, partial stabilized zirconia. Okay, so this one you can just go through, but again, you are seeing phase diagram. So in the phase diagram, you should be able to tell either is eutectic, eutectoid, peritectoid, and so on. Okay, so here you look at the phase diagram, you have what in mole percentage, not weight percentage. So read carefully the phase diagram. So this one is a MgO, and you have a loss of line on the top, always liquid. On the left is temperature. So about 2800 degrees C, you will see liquid, and then go into solid solution, cubic, tetragonal SS, and ZrO2. So if the question come out using this diagram, you just copy lah. SS means solid solution. Okay, SS means solid solution. And so on. So you already have the skill set for analyze the phase diagram. So I'll just go very far. Just a quick quiz question here. Why is it impossible to fabricate articles from pure zirconia? If you look at the phase diagram, So transformation from pure ZrO2, okay, pure HrO2 is what? Is here, 100% is here. So you can only see ZrO2 at here, maximum solubility in MgO. So if you go very small here, means something, this is 10, maybe 1 mole, 1 mole percent. Okay, this is mole percent, so it's very, very small. So it's martensite. So this one go and see the previous chapter one. Already tell you how to make martensite. There's a diagram there. Okay, cannot be suppressed by rapid cooling. Okay, the rest you read. Okay, the rest you read lah. Is self-explainable in the diagram. Okay. So I want to explain the surface fracture toughness. Fracture toughness is K, K value. This one also you read. This one you already know. Atomic defect or point defect, interstitial or vacancy. This one you know lah. And there's a Skokie fender defect. This one you already learned. Happen also in ceramics. Okay. So remember this equation. Okay, n equal to n exponential minus q divided by 2 kt. We apply the same also, right? So you've seen this one, Skokie, same, all right? Another equation for Skokie. Same presentation, only the energy here is different. Frankel, you use QF, Q Frankel. If you use Skokie, you use Q for Skokie. Q for Skokie. The rest. Okay. This is to just a forensic analysis on the source of the crack in ceramics. So as you see on the first diagram here is a point crack. So you crack from this point. This one crack from this side. So this one is cracked from here with the angle. This one also the origin. Okay. So in the ceramic, this one will be the glass in the glass. So when there's a crack there, so there will be a source of failure, and then there will be a layer of dot 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 here is the mist region. So after the if start from smooth, the mist, then go into hacker region. Okay. So this will be the surface of brittle ceramics. Brittle ceramics. So sometimes this one also will ask you to illustrate or draw the fracture surface, a typical feature observed on the fracture surface of the brittle ceramics. Okay, explain, support your answer with schematic diagram of this one. So we expect you to draw this diagram, maybe 5 marks for this to test your understanding on the fracture surface. Okay, something like this. This will be the application in the especially when you have a car, and if your front mirror cracked before, you'll see this one. So origin will be here, minor and hacker mist diagram. Okay, smooth mirror, so here. Okay, example 4, I will just assume you already know lah, how to calculate the Skokie things. So this one as your homework. Just substitute and find. Okay. Okay, we have a short break and we continue phrase diagram. Okay, stop here. 10 minutes breaks. We continue 9:05. Okay, there's an announcement for your lab, for your lab report. As what I write on the